Chapter 4, we'll start with chirality, so let's take a look here. 4.1, Introduction to Chirality. We're going to be looking here at enantiomers. Levels of organic structure. Organic compounds can be described using different levels of structure, starting with composition, the molecular formula, constitution, how the atoms are connected and their bonding patterns, configuration, which is the three-dimensional positions of atoms, and the conformation, positions of groups with respect to bond rotations and other easy processes. Each level is associated with a type of isomerism. For example, configurational isomers differ in configuration but are identical at higher levels, as we see here from the cis-1,3-dimethylcyclopentane versus the trans-1,3-dimethylcyclopentane. Chirality. A chiral molecule is not identical to its mirror image, i.e. it's not superimposable on its mirror image in 3 dimensions. A molecule which is superimposable on its mirror image is called achiral. Chiral mirror images have an interesting kind of configurational isomerism, as shown here. Molecules A and B are mirror images, but you can't superimpose them on one another. You can't align all 5 atoms in A and B. You can't rotate them so that they look the same. Therefore, A and B are both chiral. Okay. Since they are mirror images but not superimposable, they are called enantiomers. Enantiomerism is a relationship between 2 molecules. A molecule cannot be an enantiomer in isolation. Notice that the key to having enantiomers is that they are asymmetric, with 4 different carbon groups attached to a tetrahedral carbon atom. Once more, A and B are enantiomers, mirror images that are not identical. Now, identical mirror images. Many molecules are identical with their mirror images. To test, reflect the molecule through the mirror and try to superimpose the mirror image on the original. Here we have CF2ClH. We can simply slide the mirror image on top of the original to see that this molecule is achiral. Now 4.2, the Chirality Center. A carbon bonded to 4 different groups, W through Z, is called a chirality center, as shown here. When W through Z are all achiral groups and all different, C, W, X, Y, Z is a chiral compound. A chiral center can be used with care to identify a compound as chiral. Notice that some molecules with more than one chirality center may be achiral. Examples here include butanol, chiral with 4 different carbons at C2, but look at 2-propanol. 2 of the groups at C2 are the same, so it's achiral. Note that any difference in ring groups makes them distinct for the purposes of identifying chirality centers. Here, the starred carbon is a chirality center down to 4 different groups, CH3, CH2, H, and O. In the next drawing, carbon 4 is a chirality center. The chain including carbons 3 and 2 is different from the C5 to the C6 chain. 4.3, Symmetry and achiral structures. Elements of symmetry. Achiral molecules include planes of symmetry and/or inversion centers that leave the appearance of the molecule completely unchanged. A plane of symmetry, by the way, is an internal reflection plane, as shown here. An inversion center, on the other hand, is a point through which all atoms are projected. Here's a shortcut for identifying chirality. Molecules that contain planes of symmetry or inversion centers are necessarily achiral. Hence, we can look for a plane of symmetry to identify a molecule as achiral. Look hard. Be careful when applying this method. Generating the mirror image and failing to superimpose it on the original is a fail-safe method. 4.4 shows us how to recognize optical activity. Chiral compounds containing an excess of one enantiomer over the other rotate the plane of plane polarized light, as shown here. You have light source and unpolarized light with a polarizing filter. The plane polarized light oscillates in only one plane. We have a sample tube with a solution of optically active substance and may rotate the plane polarized light as shown by angle of rotation alpha and as observed at an analyzer. As shown here, optical rotation is measuring using 2 polarizing filters, one of which rotates the light. Enantiomeric mixtures may include racemic mixtures with equal quantities of enantiomers. This cancels out, and therefore the racemic mixtures are optically inactive. You can have homochiral or enantiopure, in which all the molecules in a mixture are the same handedness. You may also have an enantiomeric excess, a mixture of enantiomers where one isomer is present in larger amounts. The EE is the percent of major enantiomer minus the minor. Specific rotation and enantiomeric excess. A pure plus enantiomer rotates light in one direction, and pure minus enantiomer rotates light to the same angle in the opposite direction. Optical rotation depends on the length and concentration of the sample. Dividing these out to obtain specific rotation alpha, 100 times alpha over CL is our calculation. The specific rotation of a mixture of plus and minus enantiomers is linearly related to A for the pure enantiomer and the enantiomeric excess. So enantiomeric excess, or optical purity, is the specific rotation of the sample divided by that of the pure enantiomer and multiplied by 100. Section 4.5 looks at absolute and relative configuration. The absolute configuration of a molecule is the full specification of the three-dimensional positions of its atoms. Absolute configuration ultimately must be confirmed by X-ray crystallography. However, the relative configurations of two related compounds can be deduced if conversion of one to the other does not involve chirality centers in the compound. For example, here we see the chirality center in 3-butanol and its reaction with hydrogen and the presence of a palladium catalyst. The product is shown with its chiral center, and that's 2-butanol. Notice the alpha for each, and that the compounds do have the same relative configuration. Relative configuration and optical rotation. Compounds with the same relative configuration may have opposite signs of optical rotation. In general, the sign of optical rotation cannot be deduced from structural information alone. Our examples include 3-butanol, 33.2, and the reaction with hydrogen and a palladium catalyst. We see the 2-butanol plus 13.5, or we see the 2-methyl-1-butanol with its chiral center reacted with hydrogen bromide. Notice that alpha in one case is minus 5.8, but the product, 1-bromo-2-methylbutane, is plus 4.0 along with water. So there's a reversal there. In 4.6, we consider the Kohn-Ingold Prelog RS notation. This RS system assigns a configuration R or S to a stereocenter based on a set of prioritization rules and a standard orientation. What you want to do here is prioritize the groups by atomic number. The higher atomic number is at the first point of difference, giving it the higher priority. So, for example, we put bromine as the highest atomic number here, followed by chlorine, fluorine, and then hydrogen. And we can see how that differs in B. The RS system, too, assigns a configuration R or S to a stereocenter based on a set of prioritization rules and a standard orientation. Prioritize the rules by atomic number. Again, higher atomic number at the first point of difference is higher priority. Point the group with lowest priority 4 into the page or screen, generating a half Newman projection, and then examine the direction of rotation from 1 to 3. If it's clockwise, give it R, and counterclockwise S, as shown here. So our prioritization rules. Higher atomic number takes precedence over the lower. And then when two atoms directly attached to the chirality center are the same, compare the atoms attached to them on the basis of their atomic numbers. Precedence is determined at the first point of difference. 3. Work outward from the point of attachment, comparing all atoms attached to a particular atom before proceeding further along the chain. When working outward from the point of attachment, always evaluate substituents by one, never as a group. And an atom which is multiply bonded to an atom is considered to be replicated as a substituent on the atom. In 4.7, we consider Fischer projections. Fischer projections avoid the use of wedges and dashes, making use of a standard orientation. It's a top-down view of the tetrahedral carbon, as shown here. Horizontal arms are pointing out to hug you. Vertical bonds are pointing back away from you, as shown in the Fischer projections for our butanol and how it looks. For our RS descriptors in Fischer projections, rotate the projection so the lowest priority group is vertical, that is, pointed away from you. So for example, we show the first configuration rotating 180 degrees around the vertical axis, and the H is vertical there. This one has a clockwise rotation corresponding to an R configuration. 4.8. Consider the properties of enantiomers. Enantiomeric molecules have identical sets of internal distances, so we have the same physical properties, such as boiling point, melting point, and density. Where they do differ is in their interactions with chiral molecules or phenomena. And we see this for such substances as R plus and minus, R minus and S plus carbon. In particular, olfactory receptors are chiral, so the chirality of the molecules may affect whether you can detect them by smell. In section 4.9, we look at the chirality axis. A molecule need not have a chirality center, by the way, to be chiral. A molecule that does twist around an axis may be chiral if it lacks a plane of symmetry. The axis is called a chirality axis, and twisting about the axis interconverts the enantiomers. Biphenyls containing 4 different substituents, A, B, X, and Y, are a good example of this, and you'll note that rotation is restricted when the groups are large enough. Further, these enantiomers are also called atropic isomers. Here's some other examples of axial chirality. BiNAP, as it's called, is a very important ligand in asymmetric transition metal catalysis, and we can see the structure, including the rings and the phenyl groups. The first example of isolated atrophisomers was from 1922, as shown on the left, with these 2 different plus and minus structures. In 4.10, we view chiral molecules with 2 chirality centers. A chiral molecule with 2 stereo centers has 4 possible stereoisomers. For example, for this 2,3-dihydroxybutinoic acid, the possibilities are 1, 2, 3, and 4, respectively 2R, 3R, 2S, 3S, 2R, 3S, and 2S, 3R. 1 and 2 note are enantiomers, as are 3 and 4. You might ask yourself, what might be the relation between 1 and 3 and also 2 and 4? Diastereomers. Isomers 1 and 3 differ at some but not all of their configurations, so they're stereoisomers but not mirror images. Hence, they are diastereomers. Notice that isomers 1, 2, and 4 are also diastereomers. Here, we view the isomers of 2,3-dihydroxybutinoic acid. We see the pair that are enantiomers, the ones that are diastereomers, there are actually 3 pairs of those, and finally those that are enantiomers. Further, note that diastereomers have different physical properties. Finally, a revisit of Cis-Trans isomerism. For both cyclic compounds and alkenes, cis and trans isomers are related as diastereomers. They have the same connectivity but differ in the spatial positions of atoms and are therefore not mirror images. We see this, for example, in the 1s, 2s, 1-bromo, 2-chlorocyclopropane, and the 1r, 2r, 1-bromo, 2-chlorocyclopropane. Keep in mind that cis and trans isomers have different physical properties, including the heat of combustion, boiling point, melting point, and so forth. Okay. So we continue here, the achiral molecules with 2 chirality centers, and the stereoisomers of 2,3-butanediol. Notice that this compound has only 3 possible stereoisomers, although it has 2 chirality centers. It has a 2R, 3R, 2,3-butanediol, and the other one is 2S, 3S. However, there's a meso 2,3-butanediol, and you can see the 2 compounds with structural identity. A compound with at least 2 chirality centers that is achiral is called a meso compound. Consider here the symmetry in meso 2,3-butanediol. The eclipse conformer has a plane of symmetry, whereas the anti-conformer has a center of inversion. So meso compounds, as shown here, are achiral by definition. If you have a plane or center of symmetry in the most symmetric conformer, you're going to have a meso compound. Let's look at Fischer projections of the meso 2,3-butanediol. Of the 3 stereoisomers for 2,3-butanediol. Notice that only in the mesostereoisomer do we have a dashed line through the center of the Fischer projection, as shown on the left. It divides the molecule into 2 mirror image halves. Section 4.12 concerns molecules with multiple chirality centers. Okay. Here's info on the number of stereoisomers. As long as chirality centers are not symmetrically disposed, the number of stereoisomers associated with a particular constitution is 2 to the n, where n is the number of chirality centers. When meso compounds are possible, the number of stereoisomers is less than 2 to the n. For example, you have aldohexoses with 4 chiral centers, so 2 to the 4th, 16, would be the maximum number of stereoisomers. Section 4.13, resolution of enantiomers here. We're going to see an example of a racemic mixture and a resolving agent to give a mixture. Separating enantiomers. Enantiomers have identical physical properties, which makes separation difficult. Separation via the differential interaction of enantiomers with a chiral non-racemic substance is termed resolution. Using a chiral ammonium salt, the famous Louis Pasteur accidentally resolved the enantiomers of tartaric acid, as shown here. How to convert these enantiomers to diastereomers? The key idea of resolution is to use a chiral enantiopure substance, P+, transforming enantiomers C+, and C- as shown here into diastereomers. And then the separate diastereomers can be dissociated to a single enantiomer on both ends and recover the resolving agent. Section 4.14, chirality centers other than carbon. Any atom bonded to 4 different groups in a tetrahedral arrangement can be considered a chirality center. Notice that a lone pair can be considered as a group in its own right. So you see how this might work with S plus benzyl methyl phenylphosphine, with alanine, with esmoprazole, and with the R plus 1 naphthyl phenyl methyl silane. Amines, by the way, are achiral. Although amines with 3 different groups, such as NR1, NR2, NR3, seem to contain nitrogen as a chirality center, enantiomeric amines interconvert rapidly at room temperature, very fast. Enantiomeric amines are better thought of as conformers rather than constitutional isomers, except at low temperature. Under normal conditions, because of rapid amine inversion, amines are usually drawn as trigonal planar, their so-called average conformation.